Graphs of logarithmic functions. One way to graph a logarithmic function is to convert it into exponential form before picking your points. So to graph a logarithmic function, you can write the log function in the form y equals log base b of x. You can rewrite the function in exponential form, b to the y equals x, then choose values for y and solve for x. Plot the points and connect in a smooth curve. Here's an example, graphing y equals the log base 5 of x. So we're already in the form y equals log base b of x. So let's rewrite the function in exponential form. This is the base. So we're going to rewrite this as 5 to the thing the log is equal to, which is the exponent, to the y equals the argument x. So we make a t-table, and we're going to pick values for y and figure out what the x's are that match. So when y is 0, what is x? When y is 0, we have 5 to the 0 for x equals x. What is that? That's 1. So that means we have the point 1, 0. What about when y is 1? When y is 1, x is 5 to the first power, which is just 5. So that means we have the point 5, 1. What about when y is 2? When y is 2, x is 5 squared, which is 25. So that gives us the point 25, 2. What about when y is negative? Say negative 1. Then x is 5 to the negative 1, which is 1/5. And we'll try when y equals negative 2, x is 5 to the negative 2, which is 1 over 5 to the positive 2, which is 1/25. This is a graph of that function, and we'll see where the points line up. Here's the point 1, 0. Here's the point 5, 1. This is 1/5, negative 1, 1/25, negative 2. That's the point 1/5, negative 1. That's here. And 1/25, negative 2. That's here. If you connect these in a smooth line, you get the curve that's there. Here's some properties of the function f of x equals log base b of x that you can see from the graph. The domain of f is from 0 to infinity, from here to there. And the range is from negative infinity up to positive infinity. The graph of f has x-intercept 1, 0 and passes through the point b, 1. So that's, in this case, 5, 1. Domains of logarithmic functions. Since the base b is always positive, and whenever you take a positive number to any power, you get a positive number, the domain of logarithms are all positive real numbers. So you want to make sure that if you have a logarithm, that you never plug in anything that's negative. So the domain of a function, that is the composition of a logarithm and some other things, needs to make sure that those other things are positive. Let's look at an example. Let's find the domain of log base 6 of 5 minus x. We know that whatever goes into the logarithm has to be positive. So that means we need 5 minus x to be bigger than 0. If I solve this inequality, I add x to both sides, and I get 5 is bigger than x. So that means if I drew a picture, Here's 5. I need x to be smaller than 5, which is everything here, not including the 5. If I write that in interval notation, that's going to be from negative infinity, here on the left, all the way up to 5, not including either. So the domain is from negative infinity to 5. You can plug in anything less than 5, and you'll get an answer. Let's find the domain of log base 8 of 2x over x minus 3. Here, the restriction on the logarithm is that this whole argument is positive. So that means we need 2x. So that means we need 2x over x minus 3 to be bigger than 0. When is a fraction positive? A fraction is positive when either both the numerator and the denominator are positive, or when both the numerator and the denominator are negative. To figure out when 2x over x minus 3 is positive, we'll use the method of critical points. What are the critical points of this rational function? You get a critical point when either the numerator or the denominator is 0, because that's the only time either one can transition from negative to positive. So our critical points are any points that make the numerator 0, which is 0, and any point that makes the denominator 0, which is 3. If I draw a timeline, if I draw a number line, that means I have a critical point at 0 and a critical point at 3. We know that both of these points are excluded because at 0 this thing equals 0, which is not positive, and at 3 it's undefined, which is not positive. So now we can test points in the various regions to see what the sign is. If you plug in -1 for x, you get 2 times -1 over -1 minus 3, which is -2 over -4. That's a negative over a negative, which is a positive. So we know this point is included, this point is included, and as well as any point in this region. These are positive. If you plug in 1, you get 2 times 1 over 1 minus 3, which is 2 over -2, which is negative. -1 in particular. But all we care about is that it's negative, which makes this whole region negative. So we exclude it. If you plug in 4, you get 2 times 4 over 4 minus 3, which is 8 over 1, which is positive. So that means this 4 is included, as well as anything in the region. So this whole region is positive. If I write this domain in interval notation starting from the left, I have negative infinity up to 0, not including that 0. And then from here I have 3 up to infinity, not including either. And I want both of these regions, so I take the union. That's the domain.